Okay, so this section is double integrals and polar coordinates. So we looked at double integrals in rectangular regions, then we looked at double integrals over general regions, and then we looked at area and volume. And so now we want to look at the same integrals in polar coordinates because sometimes it is easier to do the problem in polar coordinates. So we want to recognize the format of a double integral over a polar rectangular region, evaluate a double integral in polar coordinates by using an iterated integral, recognize the format of a double integral over a general polar region, and use double integrals in polar coordinates to calculate areas and volume. Okay, so I'm going to draw this picture of a polar rectangle. All right, so basically, here's that. I'm going to draw another one that looks like that. And then I want to draw okay. So this is my region. And I want to be able to say that, as you can see, if I start and go up to here, that's going to be alpha. And then if I go all the way up to here, that's going to be beta. So as you can see, theta is between alpha and beta, not between. So theta is between alpha and beta. Okay, and so I have R equals A to R equals B. So this is R. Well, why did I draw that? Oh, this is a delta theta region. Okay, and so here, if I take, here's R is equal to A. And here is R is equal to B. Then the region I have is just this little shaded region right here. So that's called a polar rectangle. It's basically not quite a rectangle because it's rounded. So it's a polar rectangle. And then you can see that theta goes from there to there, and A is less than equal to R is less than equal to B. Okay. So if we had, so this is the area of a circular sector with radius R. So this is the area of a circular sector with radius R. Okay, so the central angle theta, so if I was to try to do the middle angle, so the central angle between them here, so this central angle theta not alpha, theta, all right? So the area of this sector is 1/2 R squared times theta. So therefore, the area of the polar rectangle is equal to 1/2. So the area of the first piece is 1/2 b squared, and its angle is beta minus alpha. So that's 1/2 b squared. That tells exactly how long it is. So that's the whole thing minus 1/2 of a squared times beta minus alpha. So this turns out to be 1/2 b squared minus a squared times beta minus alpha. But that turns out to be 1/2 a plus b times b minus a times beta minus alpha. Okay, so this piece is like the average value of R. And then beta minus alpha, well, B minus A is the change in R, and beta minus alpha is the change in theta. So the area of that little tiny piece is the average of R times delta theta. So now let's say I take another polar rectangle. And this time I'm actually going to divide it up. So I'm going to get this. And so now I'm going to take it like that, and then take it like this, and then take it like this, and then take it like this. So now I have all of these little pieces, and then the R goes like that, it goes like that. So all of these are polar rectangles. Okay, so I have a polar partition. So with this polar partition, I take A equal to R naught less than R1 less than, and I break it up into M values of R, and alpha equal to theta naught less than theta 1 less than theta n, which equals beta. So I separate this partition into these smaller pieces. So now I'm going to choose a selection. And my selection S is on each rectangle I'm going to choose an XI star and an YI star. Just like we did before. And so now we want to compute the sum I equal 1 to infinity of whatever function of XI star YI star times delta AI. Okay, so when I go to do that, that's going to equal the sum I equal 1 to infinity. F xi is going to be Ri star times the cosine of theta I star, and y is Ri star, the sine of theta I star, and dA is Ri star delta Ri delta theta I. Okay. So this now becomes that. And I'm wrong. I don't want it to go to infinity yet. I only want it to go to n. Well, let's make it k. Okay. So then the area is the limit as k goes to infinity of the sum I equal 1 to k of f of ri star cosine of theta I star ri star sine of theta I star ri star delta ri delta theta I. And as we remember, this piece always becomes an integral of f of r cosine theta, r sine theta, r dr d theta. So now our delta A or our dA is now r dr d theta. So you can't forget that r. Okay, so that's what makes the difference. Okay. So here's an example. All right, find the double integral over the region of x plus y dA, where r is the region in the first quadrant, bounded by the lines y is equal to 0, y is equal to the square root of 3x, and the circle r is equal to 2. Okay, so I'm going to draw that region for you. Okay, so I have this line, and then I have that circle. So this is my region in here. So all of that is R. Okay, so now as we can see, if we were to try to do this in Cartesian coordinates, we'd have to do two integrals. Okay, so in Cartesian coordinates, so this is the circle r is equal to 2. This is y is equal to the square root of 3x. And of course, this is y is equal to 0. So in Cartesian coordinates, I would have to split this up into two intervals. The first one, y would go from 0 to that line. And then the second piece, y would go from 0 to that circle. And then we'd have to find where they actually intersect, which is really pretty yucky. But it's easy in polar coordinates, because in polar coordinates, go back. In polar coordinates, I can draw an R. Here's my radius. I can start it down here where theta is equal to 0 and move it up until theta is equal to this value. Okay, and I can see that R always starts at 0 and goes out to 2. So R starts at 0 goes out to 2, theta starts at 0 and goes to that line. So the question is, what is that line? Okay, so far we already know that R is going to start at 0 and go to 2. Theta is going to start at 0 and go to this line. So we don't know what that is yet. Then in the place of Rx, I'm going to have R cosine theta. And in the place of Y, I'm going to have R sine theta. And in the place of dA, I'm going to have R dr d theta. So the only thing I need to figure out is that. Okay. And that's not hard to figure out because we have Y is equal to square root of 3x. So that says R sine theta is equal to the square root of 3 times R cosine theta. So if I divide, I get the tangent of theta is the square root of 3. So that says theta is pi over 3. Okay. So now I'm going to compute this integral, but I know what goes up here. Okay. So now I'm going to get the integral from 0 to 3. And on the inside, I'm going to get the integral from 0 to 2. I'm going to have R squared times the cosine of theta plus the sine of theta dr d theta, because I pulled one R in with that other one. And d theta should be in black. Okay. So now I get the integral from 0 to 3. When I integrate this, I'm going to get 1/3 R cubed. And I still have the cosine of theta. I can make this an iterated integral, actually. I can split it completely because everything's separate. So for this one, I can do the integral from 0 to pi over 3 of cosine theta plus sine theta d theta times the integral from 0 to 2 of R squared dr. I can do that only because they completely separate. So the integral from 0, this piece right here, well, that's the integral from 0 to 2 of R squared dr. That turns out to be R cubed over 3. Evaluate between 0 and 2. So that piece is just 8/3. So the piece I really have to deal with, so this now becomes 8/3. The integral from 0 to pi over 3 of the cosine of theta plus the sine of theta d theta. So that's 8/3. I'm going to get sine of theta minus the cosine of theta. Evaluate between 0 and pi over 3 as part of my last part of the answer. So this is 8/3. Then I'm going to get the root of 3 over 2 minus 1/2. And then that's the first piece. then I have to put in 0. So I put in 0, I'm going to get -1. So I have -1/2 plus 1. So that looks like 8/3 times the root of 3 over 2 minus 1/2. So I can kill off the 8. And this should be, why do I have, yep, minus, this should be plus. So therefore this becomes 4/3 times the root of 3 plus 1. And I'm done. Okay. Question?
No, not right now.
Okay. Calculate by double integration the area bounded by x squared plus y squared is less than 4. Okay, so that's a disk of radius 2. So therefore the area should be pi times 2 squared. So I should get 4 pi. Okay, so let's compute it. This is actually rather easy. Okay. So R goes from 0 to 2, and theta goes from 0 to 2 pi. Okay. So we get 0. So theta goes from 0 to 2 pi, and R goes from 0 to 2, and then we just get dA, which is R dr d theta. So that's the integral from 0 to 2 pi of d theta times the integral from 0 to 2 of R dr. So this piece is easy. That just turns out to be 2 pi. And this turns out to be 1/2 R squared, evaluated from 0 to 2. So that turns out to be 2 pi times 2. And again, we get the much desired answer of 4 pi. Okay, now let's do something harder. Problem 3. Find the volume V of the region bounded above by the plane Z is equal to 4 plus X plus 2Y, and on the sides by a cylinder X squared plus Y squared is equal to 1, and below by the XY plane. Okay, that's what we have to find. So this is X squared And this is y squared. Okay. So if I were to draw this, I would have, here's my world. I have a cylinder that looks like that. And this cylinder is as such. Okay, so I only don't have to worry about what's happening below the XY plane. And on top of it is a plane. So there's a plane up here. That's this thing. Okay, let's get rid of that. It does not let me draw stuff slanted, which is fine. There's a plane at the top. So I want the volume of that whole thing. Going around to the other side. Okay. All right. So if I look in the XY plane, all I see is a circle. Okay, come on, I want it black. In the XY plane, all I'm seeing is a circle as my boundary. I'm being bounded by this circle. So that's the same circle. So in the XY plane, I can see that R goes from 0 to 1. Theta goes from 0 to 2 pi. And my height, I'm going from 0 up to the function on top. So therefore I get the volume, the integral from 0 to 2 pi, the integral from 0 to 1, and z is 4 plus x plus 2y dA. So that becomes the integral from 0 to 2 pi, the integral from 0 to 1, and let me take this off and make that an R. Okay. So now I have 4 plus R cosine theta plus 2R sine theta, R dr d theta. Okay. So now I cannot pull this apart because I can't factor anything out. So this is the integral from 0 to 2 pi. On the inside, I have the integral from 0 to 2 of 4R plus R squared cosine of theta plus R squared times 2 sine of theta dr d theta. So I hope you see that the r was multiplied inside. So this becomes the integral from 0 to 2 pi. On the inside, I'm going to get 2r squared plus r cubed over 3 times the cosine of theta plus 2r cubed over 3 the sine of theta, evaluated between 0, and I think I made a mistake. I think I changed this to 2 by accident because of the last problem. That really is a 1 d theta. Okay. So this becomes the integral from 0 to 2 pi. And here I'm going to get 2 plus 1/3 cosine theta plus 2/3 sine of theta minus what happens when I put in 0. So I get 0. When I put in 0 for r, all of them give me 0. And then now that's what I have to integrate with respect to theta. So this becomes 2 theta plus 1/3 the sine of theta minus 2/3 the cosine of theta, all of that evaluated between 0 and 2 pi. So the 4 pi I get plus 1/3 sine of theta, that's 0, minus the cosine of 2 pi is 1. And then I need to subtract off when I put in 0. Sine of 0 is 1, cosine of 0 is that. That is not the answer I got. That's right. I'm just staring at it like it's going to change. Okay. So now here's another one. Any questions? I'm hounding you with examples. Find the volume of the solid region inside the sphere x squared plus y squared plus z squared equals 4, and outside the cylinder x squared plus y squared equals 1, and above the x, y plane. Okay. Okay. So the region is inside the sphere and outside the cylinder. That looks to me like an apple core. So let's see what we have. So we have this, and then we have a sphere. So this is the sphere. Okay, so that's the sphere of radius 2. And then we have a cylinder of radius 1. Okay. I think that by far is the best picture I've drawn this whole semester. That looks pretty awesome. We're not worried about what's happening down below. Okay. So as you can see, ha, go on, girl, that's a nice picture. Okay, so we want all the area that is outside the cylinder, but inside the sphere. So that is all of this area out here. Okay, so that's what we want. So the first thing we need to do is eyeball this thing. Okay, so eyeball it from the top and see what the XY plane looks like. So when I do that, the XY plane looks like two concentric circles. One bigger red one. And then one smaller blue one. So I have two concentric circles, otherwise known as an annulus. Okay, so on this one, in the XY plane, Z is 0. So this outer circle becomes x squared plus y squared is equal to 4. And the inner circle is x squared plus y squared is equal to 1. So this one is r equals 2, and this one is r equals 1. So the area that I want R starts here and goes there. So I can see that on the region on the ground, that theta goes between 0 and 2 pi. And R, that scared me. And R goes from 1 to 2. Okay, so that's good. Now I got to deal with the thing that's on the top. Because on the top, this thing is z squared is equal to 4 minus x squared minus y squared. So that's the function that's on the inside. So now I get the double integral over the region f of xy dA. It's going to be, R is going to go, or theta is going to go from 0 to 2 pi. R is going to go from 0, no, R goes from 1 to 2. And then the function on the inside is the square root of 4 minus, and then x squared plus y squared is just r squared, because we're trying to put everything in terms of polar coordinates. And then the area is r dr d theta. And that r is very, very helpful. So this is the integral from 0 to 2 pi d theta times the integral from 1 to 2 of the square root of r times the square root. Well, I'm not even writing as a square root. I'm going to write it as 4 minus r squared to the 1/2 power dr. Okay. So now this part's just going to give me 2 pi. And this part is going to give me, well, if I integrate that, I go to the 3/2, divide by that, that's 2/3. So I'm going to get 2/3 times 4 minus r squared to the 3/2 power. But I have to multiply by a negative 1/2. To make up for when I took the derivative, a minus 2r popped out. So should be good. Evaluated this part. Evaluate it between 1 and 2. And then I'm going to have minus 1/2 and 2/3 comes out. And now when I put in r equals 2, that is 0. And when I put in r equals 1, when I put in r equals 1, I get, took the 2/3 out. So I just get 4 minus 1, which is 3 to the 3/2 power. So now I have this 2 and that 2 divide out, this negative and that negative divide out. This 3 and one of these 3's divide out. So that just gives me 2 pi, and there should be a square root of 3 left. And that's it. Okay. So notice all of those regions that we did were simple in terms of R. No, in terms of theta. So all of the above problems were simple. All right. In terms of okay, but what do you do if it's not simple? Okay, so actually it was simple in terms of R, actually. So now suppose you have something like this. And so now it does something like that for theta. So now this is R is equal to H1 of theta. And this is R is equal to H2 of theta. Okay, so now theta still goes between alpha and beta. But now R goes between H1 of theta and H2 of theta. So now my double integral over R of f of xy dA now becomes theta goes from alpha to beta, but R goes from H1 of theta to H2 of theta, and this becomes f of R cosine theta, R sine theta, R dr d theta. Okay, so that's what we get now. So this is our volume under the surface. Z is equal to f of xy. And if I just want to compute the area, will be the integral from alpha to beta, the integral from H1 of theta to H2 of theta, R dr d theta. Okay. I don't know if I'm going to have time to finish this one. Change. I don't. I have 1 minute left.
I'm
Change.
going to finish it tomorrow.
Yep. I am going to write it down though.
Okay.
Change the integral the integral from 0 to 1, the integral from minus the square root of x minus x squared to the positive square root of x minus x squared. And the inside is x squared plus y squared dy dx. And we start there tomorrow. Okay.
Okay, see you tomorrow.
All right. See you tomorrow.